Okay, our next speaker will be Celine Lukito from New York Row. She will tell us about an introduction to topological data analysis through the lens of persistent homology.
All right. Hi, everyone. My name is Celine, and I am currently a junior here at Molloy, double majoring in math and computer science. So today I will introduce you the topic of topological data analysis, specifically through the lens of persistent homology. So, well, imagine you have two-dimensional data. Like, for example, you want to analyze the relationship between coming to class and your final exam grade. What would you do? You might find its regression line or visualize it through some figures, like you could do line graph, histogram, circle graph, or bar graph, depending on how you want to look at it. But what if you have high dimensional data with 10 variables that are affecting your analysis? It would be really hard to visualize it, let alone analyze it. And this is where topological data analysis comes in. This is just one of the many techniques out there that are available to analyze high dimensional data. But TDA has been prominent because its ability to analyze noisy and complex data. Instead of looking at it at like a local point of view, this TDA analyzes the general global idea by looking at the patterns and relationship between the data points. So the pipeline for TDA is pretty simple. There's only 4 steps. You start with data points, and then you would force it to have a shape. This is where the topology comes in. You would use the idea from algebraic topology to create these shapes. And then you could analyze its topological features, which allows you to analyze the data. But how can we ensure that when we force these shapes, that the data will still have those same properties? This is where the idea of homomorphism, the classic topology example, where donuts are has the same property as a coffee mug, because donuts can be continuously deformed into coffee mug without tearing it or cutting it. So this way we can map donuts to maybe an easier space to work it, such as a coffee mug, or the other way around. And also one thing to notice is that both of them has one hole, in which I will talk about it more in the later presentation. This has many potential because a sphere is clearly not homeomorphic to a torus because on how they physically look. And TDA can be really used because if you look at it physically, donut and coffee mug clearly do not look alike, but they have the same topological feature. And the shapes in topology are called simplicial complex. A group of simplex are called simplicial complex, and 0 simplex is just a point. 1 simplex is a line. 2 simplex is a 2D triangle, because triangle is the most basic shapes. You could create other shapes using triangles. And then 3 simplex is just a 3D triangle, a prism. And so, for example, you have data points. You would create this simplicial complex by increasing the radius of the circle. This way, you could connect the data points. And what happened if you were to increase that radius so that the circle gets bigger? You would start to see 2 simplex coming out. And you would also notice there exists a hole. But what happened if you keep increasing that radius until everything is connected? That hole might appear and might disappear. And this is really important. And you could summarize this analysis through a barcode diagram. This is called a persistent diagram, where you could filter out the noisy data from the complex data. So the data that only appears for a short period of time when you filter the data are considered to be noisy. So you could focus on the significant part of the data, such as the highlighted part. And this way, after you create those persistent diagram, you start to see some stuff that some features that are more prominent, and you could analyze those topological features. And we call that homology groups. So you would analyze the dimension of those homology groups. So if let's say, if you calculate the dimension of the zeroth homology, that would give you the number of components. The first homology would give you the number of holes in the data. H2 would give you the number of voids, which is just two-dimensional hole, while H sub k will give you k-dimensional holes. After you get those dimensions, you would be able to analyze the data. So let's look at an example. Let's say you have 5 data points, which after you increase the radius up to a certain radius, the figure will look like this. Some of them are connected, while some just not. As you can see, like the E is a separate component from the rectangle, sorry. So step 1 is to create the simplicial complex. And if you recall, simplicial complex is just a collection of those simplex. And zero simplex are points. The points that are in this example are A, B, C, D, E. 1 simplex are the lines, and 2 simplex is a triangle. Specifically, there's only 2 simplex here because the ACD is not shaded, which means it's not 2 simplex yet. If you increase the radius even more, it will become 2 simplex later. And then you would create chain groups, which is just collection of those simplex. So C sub 0 would be collection of those 0 simplex, and so on. Then after we create those simplicial complex, we could apply the boundary maps, which is basically just functions that allows you to map from a higher dimension to a lower one. So this boundary operator, so for example, del3 would map C3 to C2. Similarly, del2 will map C2 to C1, so it will bring it down to a lower dimension. So let's look at del3 in this example. Del3 would apply C3 so that you can bring it down to C2. But this is a 2-dimensional figure. There is no 3-dimensional C3. There's no 3 simplex in this figure. So it would just be del3 of 0, which is also 0. But for del2, recall that the 2 simplex in this figure is ABC. You would bring it down to C1 using the formula on the right side. And when you apply that formula, so for example, if you look at the first element, you would remove that element and put the BC. You would alternate the sign. Similarly for B, you would remove B and put AC in the answer. And you alternate sign and do the same thing for the C element. So you would repeat this for del1 to find what are the images for del1. The reason why you need this is because in the third step, we would compute homology groups in which we would need the image of del k plus 1. So homology H sub k is defined as the cycle mod by the boundary, which is also the kernel of del k. You mod that by the image of k plus 1. Kernel, as you recall from linear, it's all the x value. When you apply the function, it will map to 0. And similarly, image is just the image of that function. So let's look at H sub 0. You would get the kernel of del 0 and you mod it with the image of del 1. So what is the kernel of del 0? So look at the highlighted part. Del 0 would just be all the elements in C sub 0 that maps to 0. Well, everything in C sub 0 will map to 0 because there's no lower dimension than 0. Like 0 is the lowest dimension. So everything in the 0 dimension will map to 0. So the kernel would just be A, B, C, D, E, all of C1, is C sub 0, right? And what about the image? Image would just be image of the function, which all the yellow part. So what does this mean though? If you apply the formula for mod, you would notice that A, B, C, D, A is equal to B, which is equal to C, and also equal to D. But E doesn't cancel out. E doesn't get absorbed to the image. So you would left with A comma E as the generator in the kernel, which gives you a dimension of 2. What does this mean in terms of the example? So if you recall, H sub 0 gives you the number of components. So what are the 2 components in this example? It would just be those 2, the 2 separate components. So if you apply the same formula to H sub 1, which gives you a number of hole, you'll get 1. The hole in this example would be that triangle. Same formula for H sub 2, you'd get the number of voids, which is 2-dimensional hole. But since we are in 2-dimensional figure, there wouldn't be any 2-dimensional hole because the most that you can get is a 1-dimensional hole in a 2-dimensional figure. That's why the dimension of H sub 2 is 0. All right, so what can we do with this information? TDA is a fairly new topic where you could apply it in many different fields, such as medicine, engineering. If you're into computer vision, computer graphics, you could use TDA to analyze the pixels and how images are connected to each other, and also robotics. There are many advantages, as you can see. The calculations are fairly accessible. You would only need the knowledge in linear algebra and sum group theory. And there are also a lot of libraries out there in Python, packages in R that you could use to calculate the homology and gives you the information. And second advantage is that it looks at the big picture of the data. So instead of looking on how the data points are similar to another, you would look at the overall structure. You would look at the shape. And the third advantage is that noisy and complex data, it's easier for you to analyze noisy and complex data because you're not literally looking at each data points. You're looking at which data points would persist throughout those filtration. So you would only look at the significant part of the data. You don't really, all the noisy part will be filtered out. And lastly is the application. As you can see in the previous slide, you could apply it to your own field. But also comes with limitation because it's a fairly new topic. And since it requires algorithm, the higher dimension that you go, the cost of those algorithm will be increasing unless P equals NP can be solved, but it is still unsolvable. Also, the second limitation is the parameter, because if you remember from the persistent diagram, as you increase the radius, more points are connected. But when do we stop though? When do we regard that something is significant? How do we recognize that, oh, this is enough, we don't have to increase the radius even more? Or when is too less, something like that. And also, if you can analyze from this examples, A and R are homeomorphic to each other, and so D and O. So they both, so A and R has one hole and they have the same topological features. How do we recognize this in a data set, especially if you have a really large one? Okay, they just have one hole, but how do we differentiate between the 2 letters? Which brings me to the third point. It's fairly new, so it requires more fairly interpretation to how you want to interpret your result into your original data. So let's say you get, okay, I got 2 holes in my data. What does that mean in terms of my points, in terms of my data? And the last one, there's a lack of theoretical guarantees. You can only, so far, there's only 5 different applications that I saw in the medical field. More is coming, but this means that it would be difficult to predict the performance on how you would apply this to your own field, which there are a lot of future implications in this. There are a lot of research opportunities since it's a fairly new topic in data science. So these are my references. And yeah, do you guys have any questions?
From a topological standpoint, have you ever looked at 50 and asked for a copy mode?
No. It didn't give me. Okay, all right.
So you say this is new, right? How many
2016 was the, yeah,
this paper?
yes.
It's like our speaker.